The second component of our example active treatment scenario is the lime slurry module. Pre-manufactured lime slurry is produced off-site, typically at a commercial facility, and delivered to the treatment site as a readily usable liquid-solid suspension. In addition to commercial manufacturing facilities, some state agencies and operators have envisioned and applied the concept of producing lime slurries at larger centralized mine drainage lime treatment facilities that can then be transported to smaller and/or more remote treatment sites. The lime slurry help file discusses in detail the advantages and drawbacks of utilizing a pre-manufactured lime slurry product. Here is what the lime slurry module looks like when it is first opened. Consistent with other AMDTREAT modules, user inputs are on the left-hand side of the module and calculated outputs are on the right. The module inputs on the left-hand side are arranged into 7 sections: water quality and flow input, pre-manufactured hydrated lime slurry information, chemical consumption, equipment options and foundation conditions, annual cost items, other cost items, and finally, other annual cost items. For our example treatment site, the first step is entering the typical flow in gallons per minute and the acidity concentration in milligrams per liter. Typical flow should approximate the average flow that the system will see during an annual basis. The acidity concentration and typical flow are used to estimate chemical usage and sludge production. In our example case, we will assume that the typical flow is what we have estimated to be our mine pool pumping rate of 300 gallons a minute. The acidity concentration of the raw water at our example site is 200 milligrams per liter. Acidity represents acid released and neutralized when the base is added to achieve the treatment pH. The acidity producing species will be the hydrolysis of aluminum, ferric and ferrous iron, and manganese, the precipitation of calcite, and the deprotonation of carbonic acid and bicarbonate alkalinity. The next input section, entitled Pre-Manufactured Hydrated Lime Slurry Information, allows us to choose selections that will refine the estimated chemical consumption and cost. The percent solids, purity of the lime slurry, and dissolution efficiency must be specified. Lime slurry producers can provide potential purchasers with the percent solids and purity of their product. Default purity for the module is 93%. Commercially available pre-manufactured lime slurry percent solids generally range between 35 and 38% solid. Mixing efficiency is used to simulate the percentage of chemical being dosed that is dissolving or participating in treatment reactions. Unlike caustic soda, lime is mostly a solid suspension in water and requires mixing to promote and accelerate dissolution. If lime slurry is dosed without mechanical mixing or agitation, perhaps only 50% of the slurry solution may dissolve and the remaining will be unavailable to further react since it will be removed during solid-liquid separation. Therefore, the mixing efficiency may only be 50% to properly estimate chemical consumption. Mixing efficiency can be measured by collecting total and dissolved water samples immediately before chemical addition and after. The difference between the total and dissolved calcium provides insight to the mixing efficiency. For our example site, since we are using a reaction tank to optimize mixing, we will assume that our mixing efficiency is 85%. The chemical input section offers 3 methods to estimate the annual chemical consumption: stoichiometric, titration, and user-specified quantity. The stoichiometric method estimates the annual chemical consumption by using the information under the water quality and flow input and pre-manufactured lime slurry information headings. The method uses values for typical flow and acidity to calculate the annual loading in calcium carbonate equivalents. The program then uses the stoichiometric relationship between calcite and hydrated lime to express the acidity load in terms of hydrated lime. Then the amount is adjusted for the user-specified values for the purity and mixing efficiency to determine the annual pre-manufactured hydrated lime slurry consumption. This is the method we will select for our example sites. The titration method allows users to input the results of field or bench acidity titrations that empirically determine the required dose to achieve effluent standards. Finally, the user-specified method allows users to specify the annual pre-manufactured lime slurry consumption. This method is typically used when AMD-TREAT is being used to evaluate long-term water liability under a reverse cost modeling situation. The next module input section, entitled Equipment, has two subsections: Storage and Dispensing System and Tank Foundation and Pump Housing. The Storage and Dispensing System section has the following selection options: electric rate, slurry storage tank. The default value for slurry storage is an 8,800 gallon tank with a 10-foot diameter and 15-foot height. This tank is commonly used in eastern U.S. coal fields and can take advantage of bulk delivery and pricing of slurry. Users can enter their tank volumes ranging from 1,000 to 12,000 gallons. Slurry refill volume, a selection choice between two standard refill volumes, either 4,800 gallons or 3,900 gallons, is based upon tank or truck size. EPDM rubber tubing to dispense slurry. Users can specify the distance between the slurry tank and the dose point, and the material unit cost to estimate the quantity of ethylene propylene diene monomer EPDM tubing required. Stainless steel agitator. A mechanical mixer agitator is contained in the slurry storage tank and is used to prevent liquid-solid separation of the slurry. The users can specify runtime and motor horsepower to estimate annual electrical usage and cost. Chemical metering pump. A peristaltic metering pump equipped with a VFD is the default selection for this module. Most systems deploy an additional pump unit to serve as backup in the case of either failure or needed pump maintenance. Users can specify the number of pumps, horsepower rating, and operational timeframes. A HACK SC200 pH-based dosing controller. Users can opt to include the cost of a dispensing controller and pH probe. This can be a significant savings in both chemical consumption and corresponding sludge production by helping to avoid over-treating situations, especially in situations where the discharge flow or the acid load varies. Cellular telemetry and fees. Users can opt to include the cost of telemetry for remote monitoring of the system. Silicone rubber heat blanket. SRP heat blankets are attached to the slurry storage tank and thermostatically controlled to prevent freezing. 4 2x3 foot blankets are required for the standard 8,800 gallon storage tank. Users can specify the number of hours per day of operation at temperatures less than 40 degrees Fahrenheit. Tubing heat trace. Heat trace is necessary for the EDPM rubber dose tubing to prevent freezing in winter months at temperatures less than 40 degrees Fahrenheit. Users can specify the number of hours per day of operation. For our example site, we will keep all of the default settings in this section. The tank foundation and pump housing section offers choices to develop cost estimates for the slurry tank concrete foundation and also for a shed control structure to house electrical panels, pumps, and controllers. Slurry tank foundation and foundation area. Choices include the option to either specify foundation size or have AMD-TREAT estimate the foundation size. The size and cost information is reported in the sizing summary portion of the module. AMD-TREAT assumes the foundation is square-shaped, having a width and length that are 2 feet more than the tank diameter. Concrete thicknesses can also be entered. The program then provides a calculated foundation volume with the summary sizing output section. Pump and electrical control panel housing. This equipment can either be specified for outdoor use or AMD-TREAT has an optional prefabricated wooden structure to house electrical control panels. Again, for our sample site, we will keep all default settings for this section. For the annual cost input section, for our example, we will change 2 of the default values. For heat tracing operational time, we will increase the value to 10 hours per day, and for the unit cost of electricity, we will change the value from the default of 20 cents per kilowatt hour to 8 cents per kilowatt hour, which is more reflective of commercial electric rates in the vicinity of our example treatment system and is also consistent with the electrical cost value that was included in Module 1, the pumping module. The final two input sections of the lime slurry module are other capital and other annual costs, respectively. Both sections allow for inclusion of atypical capital or annual cost items for a particular treatment system. One such example could be the capital costs associated with an electronic surveillance system for the treatment site. If that system has annual fees associated with remote monitoring, this would be an example of another annual cost that could be accounted for within this section. For the purposes of our example, we will not include any additional capital or annual items. We now have entered all of the input information needed to generate the output summarized on the right side of the lime slurry module. The sizing summary at the top right displays important calculated module outputs such as the estimated daily and annual chemical consumption, the lime slurry tank refill requirements and reserve capacity, and the foundation size. The calculations indicating the days of treatment afforded by each truckload delivery of lime slurry and reserve tank capacity will indicate how often the storage tank will need to be refilled. In addition, foundation information and clearing and grubbing calculations is provided. Note that clearing and grubbing acres are reported as 0 for our example site. This results from the fact that the slurry tank foundation area and the 8x10 shed footprint does not add up to 0.01 acres or 435 square feet. Subsequent versions of the AMDTREAT software will be modified to show the value in square foot or to the thousandths of an acre. The next section on the right side of the module is capital cost, which displays the equipment cost, foundation cost, building cost, and the cost of system installation. Installation costs can be specified as a percentage of other capital costs, or the user can specify a known cost. For our example site, we will opt to change the default percentage of cost of 40% to 15%, as this is a lime slurry system comprised primarily of pre-manufacturing components that require minimal installation and on-site setup. The annual cost displays and summarizes chemical cost, annual operation and maintenance cost, which can be calculated as a percentage of the capital cost, or a known value can be entered. Electrical cost as well can either be calculated by the program or entered by the user as a known value. Other annual cost values are included and summarized if input was provided under the other annual cost section. The last section is the net present value section. There are 8 items included by default to calculate the net present value for the lime slurry module, including default values for life cycle and replacement percent for each item. The capital cost for each item is automatically used, so if the cost for any of the items is $0, it will not be included in the net present value calculation, or the user can uncheck the box next to each item if they do not wish to include that item in the net present value calculation. For our example, we will leave all of the items included and not change any of the default values. The resulting net present value for the lime slurry component is $942,943. This means that an initial investment of $942,943 under an inflation rate of 3.1% and rate of return of 8.45% is predicted to provide the funding needed to sustain slurry component of the treatment system for a 75-year period, including all operation and maintenance and future replacement costs for the system. This concludes the lime slurry section of this tutorial. Next we will discuss the reaction tank module in the active treatment tutorial entitled Module 3 Reaction Tank. Thank you, and once again please refer to the module tooltips and online help files for additional information.